Have you ever wondered what the biggest hurdle is for building powerful quantum computers? It is not just about making more quantum bits or qubits, it is about keeping them stable. Error strategies in quantum computing balance performance and resource cost by making a critical trade-off, enhancing the reliability of delicate quantum computations versus the significant overhead required to protect quantum information. Achieving better performance, meaning more accurate and longer computations, almost always demands a higher investment in physical qubits and complex control mechanisms. The fundamental reason for this delicate balance lies in the extreme fragility of quantum states. Unlike classical bits that are either 0 or 1, quantum bits can exist in superpositions of both states simultaneously. This quantum information is incredibly sensitive to environmental noise, which can cause errors like bit flips, where a 0 becomes a 1 or vice versa, and phase flips, which subtly alter the quantum state's phase. These errors corrupt the computation. To combat this, quantum error correction codes encode one logical qubit into many physical qubits, creating redundancy. This redundancy allows the system to detect and correct errors without directly measuring the fragile quantum state, which would destroy the superposition. However, each additional physical qubit and the complex quantum gates required for encoding and decoding errors, representing a significant resource cost. This includes more hardware, more energy, and more computational time. Understanding this trade-off means recognizing that every choice in error mitigation or correction directly impacts the total resources needed. Simpler error mitigation techniques, for example, might accept a certain level of error and attempt to correct it through post-processing, requiring less hardware but limiting computation depth. More robust quantum error correction, on the other hand, demands many physical qubits per logical qubit, ensuring high fidelity but at a much steeper cost in engineering complexity and operational resources. A key concept here is the fault tolerance threshold, which refers to the maximum physical error rate that can be tolerated while still allowing for arbitrary long and accurate quantum computations. Achieving operation below this threshold is critical for building truly useful quantum computers. It requires a deep interplay between theoretical code design and practical hardware engineering, where every improvement in qubit coherence or gate fidelity can reduce the overhead required by error correction. This constant push for better hardware performance directly lessens the resource burden for maintaining computational accuracy. Ultimately, error strategies define the path from noisy, intermediate-scale quantum devices to powerful, fault-tolerant quantum computers. By carefully balancing the protection of quantum information with the available physical and computational resources, researchers and engineers can progressively unlock the full potential of quantum algorithms, enabling breakthroughs across science and technology.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.